Hello and welcome to Calc Lesson number 6. Today we are going to be finishing up section 1.4, doing our second part of continuity. In our last lesson, we looked at continuity on an open interval. Today we're going to be looking at continuity on a closed interval. So in order for us to understand continuity on a closed interval, we first need to recall those one-sided limits. So remember, we have two different notations. The limit as x approaches c with this plus superscript means from the right or from our values that are greater than c, and the limit as x approaches c with this minus sign as our superscript means as we're approaching c from the left-hand side or from values that are less than c. So if we look at our quick reminder here, we want to find the limit of f of x equals 4 minus x squared as x approaches negative 2 from the right. So the way we would write that is the limit as x approaches negative 2 with that plus sign superscript of our function. And then on our graph, we can look at what's happening as our x values are approaching negative 2 from the right, meaning from those values that are greater than negative 2, our function is getting closer and closer to 0. So remember, we only care about that one-sided limit here. So when we're looking at one-sided limits, a function that we're going to start to see a lot of is the step function. So here we want to look specifically at our greatest integer function, which is denoted with these brackets. So this is the parent function, so hopefully you can visualize this from using it before, but as we continue through this section and through this year, we might start to see different transformations of this function, so it might be helpful for us to know how to actually type this inside our graphing calculator. So if you want to go ahead and grab your graphing calculator, I'm going to go ahead over the steps now for how we could type it in. So once you have your calculator, we're going to be graphing this, so the first thing you want to do is make sure you go to your y equals menu. Then once you're in y1, in order to graph this function or to get those brackets, we want to use the math button. And then we want to use the arrow key to scroll over to the menu titled num. Then from there you should have a list. Now depending on the version of your calculator, it should be numbers like 5 or 6. So on my calculator I have TI-84 plus CE edition. My menu number is number 5. And it's labeled as INT or int with a parenthesis. Once you click that, again, depending on the version of your calculator, it will either write INT parenthesis or it will actually come up with those brackets. So depending on your calculator, either way, you can go ahead and enter whatever you need inside those brackets. And then if you have the parenthesis, just make sure to close it before adding anything you need on the outside. In this case, we're just going to add an x because that's all that we have. But like I said, we might start looking at different transformations of this parent function. From there, you can go ahead and graph, and hopefully you see the step function graph that we have listed here for us. Now from here, we want to go ahead and find our limit as x approaches 0 from the left of this function, and also our limit as x approaches 0 from the right of this function. So using the graph, as we look at the limit as x approaches 0 from the left, we're looking as the x values are less than 0, our function is approaching negative 1. If we look at the limit as x approaches 0 from the right, that means from the x values that are greater than 0, our function is approaching 0. So because the left-hand limit does not equal the right-hand limit, we could actually say that the greatest integer function has a discontinuity at x equals 0. And then by similar reasoning, we could actually say that the greatest integer function is going to have a discontinuity at every integer n. The concept of a one-sided limit allows you to extend the definition of continuity to closed intervals. So here you have the formal definition of a closed interval, but basically a function is continuous on a closed interval when it is continuous in the interior of the interval and exhibits one-sided continuity at both endpoints. So let's look at an example. Here we have the function, the square root of 1 minus x squared, and we want to discuss the continuity of this function. So the first thing we want to check is the continuity on the open interval from -1 to 1. Thinking back to our last lesson, between -1 and 1, we have no holes, no gaps, no jumps, and we can draw the entire function without picking up our pencil. So our function is continuous on the open interval from -1 to 1. Now we want to look at the one-sided continuity on both sides. So let's start by looking at the limit as x approaches -1 from the right of this function. From the right, which meaning remember from values greater than -1, our function is approaching 0. And that is also where our function is defined, so that's equal to f of -1. So we have one-sided continuity on the right. We also want to look at the limit as x approaches -1 from the left of this function. Looking from x values, looking +1 from the left, because we want to look at this side of our function. Looking at values that are less than 1, our function is approaching 0. And because our function is defined at this point 1, 0, that's also equal to the point 1, 0, or where f is defined, f of 1, which means that this function is continuous from the left. So because we are continuous in the open interval from -1 to 1, and then continuous on both sides, we can say that this function, f of x, is continuous on the closed interval from -1 to 1. A few lessons ago, we studied several properties of limits. Each of these properties yields a corresponding property pertaining to the continuity of a function. If b is a real number and f and g are continuous at x equals c, then each of these 4 functions below are also continuous at c, including the scalar multiple, the sum or difference, the product, and the quotient. It is important for us to be able to recognize functions that are continuous at every point in their domain. So here's a list of 4 types of functions that we have already worked with: polynomials, rational functions, radical functions, and trig functions, all of which are continuous at every point in their domain. So for A, B, and C, we just want to discuss the continuity of each of them. Looking at letter A, our function f of x is a sum of a linear function, which is a polynomial, and a trig function. Since both x and sine of x are continuous for every point in their domain, the property in the last slide said that this function will be continuous at every point in its domain. For part B, we have the function equals 3 times tangent of x. So here we have a scalar multiple of 3 times our trig function, tangent of x. The last slide said that the property will apply and this function will be continuous at every point in its domain. And finally, for part C, we have f of x equals x squared plus 1, which is a polynomial function, over cosine of x. So here we have a quotient of 2 functions that we know both are continuous at every point in their domain. So the last slide allows us to say that this whole function f of x will be continuous at every point in its domain. And all 3 of these follows from that last slide, all of those properties that we can use for limits and continuity. So here we want to describe the intervals on which our function is continuous. And the function we're working with here is f of x equals tangent of x. Thinking back to the last couple of slides, because this is a trig function, we know that tangent of x is continuous at every point in its domain. So we have to think about our function and what values are not going to be in the domain. Thinking about the graph of tangent of x, we know that we have asymptotes, or places that tangent of x is undefined. Those include here at pi over 2, 3 pi over 2, and so on. So we can say our function, tangent of x, is undefined at x equals pi over 2, and then if we add pi, or if we add 2 pi, or if we add 3 pi, so we would write that as plus n times pi, where n is just an integer. So to write the intervals right? Because everywhere else we could see our function would be continuous. So to write the intervals of continuity, we would say tangent of x is continuous on the open intervals from negative 3 pi over 2 until negative pi over 2, separated by those two asymptotes. Again, from negative pi over 2 to pi over 2. Again, from pi over 2 to 3 pi over 2, and so on. And that's actually going to go in both directions. We also might be asked to look at limits or continuity of a piecewise function. So here we want to determine the limit of f of x as x approaches 1 for this piecewise function, where we have x cubed plus 1 if x is less than 1, and x plus 1 if x is greater than or equal to 1. This is a pretty simple function for us to visualize in our heads or for us to plug in and know what's going on, but we might come across some more exciting functions where we want to use our calculator. So we're going to use this function to practice typing our piecewise functions into our calculator. So again, if you don't have yours already and you want to go ahead and grab it, you can do that now. And then we're going to go through the steps of how to actually type in your piecewise function if you don't know. So the first thing you're going to do on your calculator is go to the regular y equals menu. Because we're graphing, we want to make sure that we're typing this somewhere where it's going to graph. Then we're going to click on the alpha button, which is right underneath second. We're going to click y equals again and then enter. Enter would be on number 1, which is n/d, which is going to give you that template. It looks like a fraction. You're going to go ahead and type the first piece of your function, x cubed plus 1, in the numerator of that fraction, and then you're going to type the parameter, that x minus 1, into the denominator of that fraction template that has showed up in y1. In order to get that less than symbol or any other symbols like that, you can click on second math, and that should give you a menu of symbols. And then you want to go ahead and repeat in y2 and y3 for however many other pieces of your function that you need. Once you've done that, you can go ahead and choose an appropriate window and graph your function. Hopefully, if you followed along, you got something that looks like this on your screen. Like I said, this piecewise function is a little easier for us to visualize, but we want to be sure we're able to type it into our calculator. There is a whole section of the homework that's going to ask you to just type into your calculator to find the answer. From here, we want to determine the limit as f of x, or as x approaches 1. So we want to look from both sides. So I'm going to look at the limit as x approaches 1 from the left of this function. Using my graph, now that I've graphed it, I can look at what's happening from values less than positive 1. From the left, I'm approaching 2. We also want to look at the limit as x approaches 1 from the right of this function. It's kind of a big plus sign. From the right, again, using my graph, I'm also approaching 2. So we can say that the limit as x approaches 1 of this function is equal to 2, since our left-hand side limit is equal to our right-hand side limit. We also want to talk about continuity of composite functions. So formally, if g is continuous at c and f is continuous at g of c, then the composite function given by f of g of x is continuous at c. So here's our example. Let's describe the intervals on which the function h of x, which is f of g of x, is continuous, given that f of x equals 5x plus 1 and g of x equals x cubed. So for these, we want to look at each individual function. So to start by looking at f of x is 5x plus 1, which is a linear function, which we know is continuous everywhere from negative infinity to positive infinity. Thinking about g of x is our cubic function, which is also continuous everywhere from negative infinity to positive infinity. Thinking about h of x, which is just f of g of x. In this case, when we look at f of g of x, which is x cubed, we get 5x cubed plus 1. Since both functions are continuous everywhere, h of x is also continuous everywhere. Okay, the last type of problem we're going to look at today is where we actually have to find a constant value that's going to make our function continuous. So here we want to find the constant a such that the function is continuous on the entire real number line, where our function is a piecewise function, 3x cubed when x is less than or equal to 1, and ax plus 5 when x is greater than 1. Just looking at the piecewise function, we can see that our possible discontinuity, the place where our function is going to possibly have a jump or a gap of some sort, would happen at x equals 1. So we need to make sure to fill in an a value that's going to make this function continuous at x equals 1. Remember, to be continuous at x equals 1, the limit as x approaches 1 of this function needs to exist. F of 1 needs to be defined. And the limit as x approaches 1 of this function needs to be equal to f of 1. So we need to make sure that we're satisfying all three of these conditions. First, let's look if f of 1 is defined. If we plug 1 into this function, because we are less than or equal to 1 for this parameter, we would plug into 3 times 1 cubed, which is 3 times 1, which is just 3. So f of 1 is equal to 3, and it is defined. Next, we need to make sure that our limit as x goes to 1 exists. In order for our limit to exist, remember that means that the limit as x approaches 1 from the left is equal to the limit as x approaches 1 from the right. Because we already have this piece defined, 3x cubed, when x is less than or equal to 1, we know that the limit as x approaches 1 from the left, we would plug our 1 direct substitution into that function, and we would get 3. So our task is to define our function ax plus 5 so that the limit as x approaches 1 from the right of this function is equal to 3. So we need, when we direct substitute ax or x equals 1 into that function, a times 1 plus 5, that needs to equal 3. So simplifying, we have a plus 5 equals 3, so we get a equals negative 2. When we plug in a equals negative 2, then our limit as x approaches 1 from the right equals 3, so our limit exists. And then because the limit equals 3 and the function f of 1 equals 3, our limit as x approaches 1 of this function is equal to f of 1, so we've satisfied all three conditions. So the constant value a that makes this function continuous on our entire real number line is a equals negative 2. Great job! Homework number 6 is actually in two different sets. So the first set, numbers 61, 65, 69, 72, 74, 75, and then 77 through 80. And then the second set, you're actually going to use a graphing calculator for all of these. And you're just going to do 14, 22, 24, 25, 73, and 82. If you have any questions, you can reach out to your teacher.